Hi everybody, this is going to be a continuation of the endocrine system. We're going to start our discussion now of the hypothalamus and pituitary gland. This is part 1, and if you'll pick up on your course pack, page 6, that's where we'll begin. So the hypothalamus has many roles. In Bio 210, you may have learned about some of those roles, including being the control center for thirst, a control center for hunger. We also know the hypothalamus regulates the autonomic nervous system, but today we're going to talk about how the hypothalamus makes and releases hormones that target the anterior pituitary gland. Now, in this picture, you'll notice the hypothalamus right here is a portion up here, and there's a connection called the infundibulum that carries us down to the pituitary gland down below. Now, the pituitary gland is divided in half. There's an anterior portion called the anterior pituitary. It is made up of epithelial tissue, otherwise known as endocrine tissue. And then the posterior portion, it's made up of nervous tissue. So a little different construction there, and that drives how these particular tissues will end up functioning. Now, I should also mention the sella turcica. You may recall the name of that saddle in the sphenoid bone. It's where that pituitary gland sits and is housed within the brain. So the hypothalamus ultimately regulates what's happening in the anterior pituitary. It actually makes hormones released by the posterior. We're going to save the posterior pituitary for just a few moments. We will come back and talk about that portion of the pituitary gland. For now, let's focus on these two terms, releasing hormones and inhibiting hormones. Releasing hormones are hormones that come from the hypothalamus, and they encourage or increase the release of hormones in the anterior pituitary. It's kind of like a gas pedal, speed it up, increase, encourage, enhance. What do you think inhibiting hormones from the hypothalamus tell the anterior pituitary? These hormones tell the anterior pituitary to decrease, slow down, or inhibit the production and release of its hormones. When you see hormone names, you will notice RH represents the releasing hormones and IH represents those inhibiting hormones. Just something good to look out for, a great reminder there. So, some of the material in Bio 211 is worthy of memorization. This is one thing that I would advocate you get stuck in your brain, just keep it close by, that releasing hormones with an RH ending and inhibiting hormones with an IH ending for our discussion today are made by the hypothalamus. Their target is the anterior pituitary. I'll tell you why this is an easy thing to remember. Instead of memorizing a list of releasing hormones and a list of inhibiting hormones, the ones we discussed today, you'll just know they're made by the hypothalamus. They will target the anterior pituitary. Now, of course, there is a disclaimer. There are other releasing and inhibiting hormones that come from other parts of your body. So this particular rule only pertains to our discussion today. See why I mentioned the rule? You don't want to memorize this list, right? But here's the easy thing. All of these terms have the RH ending for releasing hormone or IH ending for inhibiting hormone. How easy is this? These hormones all come from the hypothalamus, and their target is what? The target is the anterior pituitary. Okay, so growth hormone, thyroid releasing hormone, corticotropic releasing, gonadotropic releasing, prolactin releasing, and prolactin inhibiting. We're not talking about every single releasing and inhibiting hormone that comes from the hypothalamus. This is the list that we'll instead focus on. So if you keep these straight, RH and IH come from the hypothalamus. They will target the anterior pituitary. So we've talked about this first bullet point. The hypothalamus makes and releases releasing hormone and inhibiting hormones to target the anterior pituitary. I can't emphasize enough that this is something that you want to remember. The target organ, of course, is anterior pituitary there. We're also going to talk about this second set of bullet points. The hypothalamus also makes a hormone called oxytocin. It's abbreviated as OXY. And another one called antidiuretic hormone. It's abbreviated ADH. We'll talk in more detail about these hormones in another PowerPoint. For now, we will just know the hypothalamus makes these hormones, but they are stored in the posterior pituitary until they're released. Okay, so all the posterior pituitary does is release oxytocin and ADH. I'll make a note here and I'll remind you later, the posterior pituitary makes no hormones of its own. Okay, so that's an important thing to remember. The posterior pituitary doesn't actually make any hormones, it simply releases oxytocin and ADH for the hypothalamus. So we'll come back and come to this conversation in our next PowerPoint. So let's talk one more time about the hypothalamus and pituitary relationship. Do you recall the type of tissue that makes up the anterior pituitary? It's epithelial tissue, and specifically it's endocrine tissue. So thinking back to Bio 210, what do you know about the growth rate and repair rate for epithelial tissue? That's a tissue that repairs quickly. Now, by comparison, posterior pituitary is made up of nervous tissue. What do you know about its ability to repair? It's very poor to repair and to heal itself. Now, I wanted to make that point because in a case where someone might have the pituitary gland removed, which portion do you think is more likely to grow back? The anterior pituitary, because it's made up of epithelial tissue. Now, since the posterior pituitary is nervous tissue, it does not make its own hormones. Instead, you'll notice these neurons connecting here with the hypothalamus. These are long axons. Down here are axon terminals. Those axon terminals release neurotransmitters called ADH and oxytocin, which hit the bloodstream, and so they're now technically called hormones, right? And so those hormones travel the bloodstream and target the body's target areas. So keep in mind, the anterior pituitary does make hormones, but the posterior pituitary does not. So we're going to focus right now on the anterior pituitary. It is sometimes called the adenohypophysis because it's made of adrenal, or not adrenal, but endocrine gland tissue. So these are anterior pituitary hormones, and I recommend for this chapter, starting now, you use flashcards. On those flashcards, you might write on one side anterior pituitary hormones, and on the flip side, write these 6 hormones down. Then, if you look in your course pack on page 7, you'll notice each hormone is listed in a cascading effect of hypothalamic hormones, anterior pituitary hormones, the ultimate result when it hits the target cell or target organ. And then I would work through those slides on page 7 as a way to make yourself another set of flashcards. Here's another helpful clue. The SH and TH endings often indicate that we're dealing with stimulating hormones or tropic hormones. And so we oftentimes do see these coming from the anterior pituitary area. Not a hard and fast rule. You may see stimulating or tropic hormones coming elsewhere in the body, but that's what we're going to look at in terms of this discussion today. So we're getting ready to talk about growth hormone, thyroid stimulating hormone, or TSH, adrenocorticotropic hormone, or ACTH. Gonadotropins stimulate the gonads. They are follicle stimulating hormone, or FSH, luteinizing hormone, or LH. The final anterior pituitary hormone we'll discuss is called prolactin. It's abbreviated as PRL for short. So here's our second major rule to remember. In our discussion today, when you see SH or TH, these types of hormones are made by the anterior pituitary. They target some other gland or organ of the body. They're very similar in how they operate. We won't go into the difference between a stimulating hormone versus a tropic hormone, but we'll just generalize and say these hormones typically target some other gland of the body. Okay, so Tropic hormones are made by the anterior pituitary. Thyroid stimulating hormone is a great example here. It stimulates the thyroid gland, that is another gland of the body, to produce a hormone called thyroxine. Just a reminder, these anterior pituitary hormones are in fact all protein-based. So do they utilize the direct gene activation mechanism, or do they use secondary messenger? All right, so take a look. There's the receptor. It sits on the plasma membrane of the cell. And of course, that protein hormone is too big to enter the cell. So the protein hormone docks with that receptor, and it behaves as the first of two messengers. You may recall that inside that target cell, we're going to activate something called CAMP, and it will turn on an enzyme called protein kinase. All right, so this is the secondary messenger system. And that's how these proteins operate. So let's talk about growth hormone. If you'll flip on over to page 7 with me, the first box on the top of that page discusses growth hormone, or GH. Growth hormone is produced by the pituitary gland. Which portion? Anterior or posterior? Anterior. Okay, so growth hormone targets all cells of the body, especially we see growth occur in long bones, skeletal muscles, and the liver. That's where we see a marked increase in the size or the shape or the length of those organs. Most cells in the body have receptors for growth hormone. Because it is a protein-based hormone, that receptor is found on the plasma membrane. So there is growth, increase in size, that we expect to see when growth hormone targets these cells and tissues. So when you sleep at night, that's when growth hormone levels increase. What do you think happens for somebody who works different shifts? Third shift sometimes, first shift the next week. How do you think this kind of sleep pattern influences growth hormone levels? As you might imagine, it interferes with our ability to sleep and to grow. So this is one reason that parents want to put kids to bed at night. We know that when they get their sleep, that their bodies will grow properly. So here's something to look at. The hypothalamus produces a hormone called growth hormone releasing hormone. That GHRH targets the anterior pituitary. We knew that, right? We knew that releasing hormones are always made here in our discussion today by the hypothalamus. They'll target the anterior pituitary. In response, the anterior pituitary produces growth hormone. Growth hormone targets your body cells. Your body cells will increase in size. Okay, so it's important to keep straight the steps here. Hypothalamus, anterior pituitary, and the target are your body cells. Okay, and of course we're looking at growth hormone releasing hormone, then growth hormone produced by the anterior pituitary. There is something called growth hormone inhibiting hormone, and as you might imagine, the word inhibit means to stop. So this particular hormone stops growth hormone from being released from the anterior pituitary. An alternate name for it is somatostatin. We oftentimes hear about that particular hormone rather than its other name, GHIH. I wanted to share this with you because you've seen it before, probably in Bio 210. You're looking at the cell cycle. A typical cell cycle has a short time period for mitosis. That's when the cell divides. That's this M phase right there. The rest of the cell cycle includes G1, an S phase, and G2. Now, that G makes sense. We oftentimes call that G time period a gap or a growth time period. Guess where growth hormone exerts its effects? It's during these G1 and G2 cycles of this entire life cycle of a cell. So now we know when a cell completes mitosis and enters G1 and then cycles around into G2, that cell is responding to the effects of growth hormone. So we use, of course, growth hormone to repair and build new cells. We use it to make and grow our bodies. So growth hormone is certainly one that most cells have a receptor for. Let's Let's spend a few minutes talking about some growth hormone disorders. I've left you a question on your worksheet. What is the cause of each of these? Let me pause here and let you write down that gigantism or giantism is due to excess growth hormone. We know that hypersecretion, hyper means excess in this case, too much growth hormone can cause too much growth, especially in a child. Acromegaly means enlargement, that's mega, right, of the extremities. That's acro. So in this condition, we see excess or hypersecretion of growth hormone during the adult years. Thinking back to Bio 210, around what age do those epiphyseal plates harden and become epiphyseal lines? That occurs typically in the late teenage to early 20s. So we tend to see those bones harden and we no longer have lengthwise growth occurring after about age 20 or so. So when we see gigantism, we expect to have actively dividing growth plates or epiphyseal plates. But once those plates harden, we can no longer get lengthening of the bones. Instead, we see the bones become wider, and that's what happens with acromegaly. We see the hands and the feet and the facial bones enlarge. Pituitary dwarfism is the lack of growth hormone in a child. Of course, we call that condition hyposecretion because of the deficiency of growth hormone. On the far left, we have an individual with gigantism. You'll notice he's much taller than the normal individuals in the middle. Gigantism can produce people who have 6 foot plus, 7 foot plus, 8 foot plus range. In fact, over the time of history, there have been cases where people have been 11 feet or even 14 feet tall. So gigantism can come from changes in genes. We may have a family where everyone is exceedingly tall. And unfortunately, gigantism doesn't produce strong individuals. It puts a lot of strain on the joints to handle such a big body. In fact, people with gigantism may have trouble breathing. They may also have trouble getting around because of the strain and wear and tear on their joints. The heart is also strained because it may have been produced for a 5-foot tall body, but is operating in a 7.5-foot tall body. Andre the Giant, here on the right, had both gigantism and acromegaly. He passed away some years ago from problems in the cardiovascular system, probably due to the strain that his size put on his body's heart and blood vessels. So here's the deal. If you had gigantism, he would have had that as a child. But as his bones began to harden and no longer could growth occur in the epiphyseal plate, the only way growth could occur would be appositionally. What does that term mean? Appositional growth means the bones would only grow wider. So as he aged, his bones continued to grow, they just grew thicker instead of longer. So we tend to see acromegaly show up in the facial features, the hands and the feet. Why in those locations? Well, there's less flesh covering the fingers and the toes, so it's much more obvious if those particular bones grow wider instead of longer. Modern times, most of our tallest women cap out in the upper 7-foot range. And again, people die because of the stress it puts on the cardiovascular and respiratory systems, and also the stress on the joints. Yao Ming had gigantism. He's, of course, still around at this time, but he had incredible problems with joints, again, due to the body size. 7'6" is a lot of stress to put on those joints. This man is our tallest man in recorded history, and at 8'11", he was actually still growing. That's unusual because he was age 22. What has normally happened to most people by age 22? They've gone through puberty. Now, had he gone through puberty, that would have stopped his lengthening, and his body would have no longer grown taller. His bones would have widened through appositional growth instead. So, back in the time period when he lived, which was 1918 to 1940, they may not have known that giving testosterone would have slowed down the lengthening of his bones. Testosterone would have forced him through puberty, and puberty forces those epiphyseal plates to close. He's actually pictured here with his dad, And if you've been to Myrtle Beach, at Main Myrtle Beach, where they've got the Ripley's Believe It or Not, there is a figure of him out by the street. You don't have to pay to go in to see him. He actually toured with the circus back during his lifetime. Very unfortunate situation. He died from a blister that became infected due to leg braces he was wearing. He actually is buried in a huge concrete vault in Alton, Illinois. Of course, they didn't want people to dig up his body and parade it around as part of a show. So he is called the Alton Giant. A really sad situation there for this guy. But, you know, had he continued to live, who knows how tall he would have continued to grow. 8'11" at the time of his death, age 22. Here's a set of hands with acromegaly. You'll notice the enlargement. Acromegaly means enlargement of the extremities. We do tend to see this in people as they age past the early 20s and those who have hypersecretion of growth hormone. So it's not something you wake up tomorrow and say, wow, I think I've got acromegaly. People oftentimes notice it in pictures. They'll see a change in themselves over, say, the course of 5 or 10 years. Look at this man's change in his facial features. His brow line, his nasal bones, his jawline all seem to have become larger, and he's showing his hands because they too have enlarged due to increased appositional growth. You would not necessarily notice appositional growth increasing on your arms or your legs. There's a lot of flesh and tissue that hide those bones. Another case of acromegaly. And an unfortunate case here for a woman with acromegaly. Notice how it's changed her facial features and her hands as she's aged. Now, nowadays, what would they do for a person who's got this condition? Well, this is due to excess growth hormone. So how do you shut off growth hormone? You could use GHIH. That's the inhibiting hormone. That might do the trick in shutting down growth hormone coming from the anterior pituitary. If that doesn't work, they can also snip out the anterior pituitary through surgery. They actually go up through the nose, break a bone, and go back into the brain, remove the anterior pituitary. But as we're getting ready to learn, there is a lot of hormones that would be affected without this particular one in place. On the other end of the scale is pituitary dwarfism. So in this picture, we actually have somebody with hypothyroidism first. That's this one here. The next two people here are what we call pituitary dwarfs. They look like they have child-sized bodies, and that's because they lack growth hormone when they were growing up. Once they reach puberty and pass through that time period where their bones harden at the epiphyseal plate, there is no more opportunity for lengthwise growth of those bones. Now, had they been given some additional growth hormone during their growing years, it is possible they could have grown to a more normal height. Dwarfism is someone below 4'7", so had this been caught early enough in their lifetime, they might have been able to grow past 4'7" with injections of growth hormone. The next two people here, these two have something called achondroplasia. Notice they have normal-sized torsos, but they have shortened legs. They look different in their build from the two people on their left, well, their right, here, that have pituitary dwarfism. So in these cases, achondroplasia, we can't really give growth hormone because either the plates are unresponsive to it or there's something else going on. There's actually 100 different forms of achondroplasia that can cause dwarfism. So if you've seen the TLC show, Little People, Big World, that is the form of dwarfism that they have. So we specifically call people with pituitary dwarfism pituitary dwarfs because it indicates a decreased level of growth hormone when they were growing up. This is a great time to review some material we've covered so far in this course. In the previous PowerPoint slideshow, we talked about this problem here. Hormones that have the same effect when working together. What are they called? The clue word is same, right? And so same means they are synergists. This should be letter A. Just to go through the other questions there, permissiveness occurs when one hormone gives permission for another to do its job, and antagonists do opposite jobs. Here's another review question. Calcitonin and parathyroid hormone perform opposite actions. There's our clue word once again, right? So what are we looking at? This time we're talking about antagonist. And then finally, we've already talked about secondary messenger system. That's a way that protein-based hormones operate. So let's put a check there. Do you see any others we should check off? Well, we know that protein-based hormones turn on CAMP. So let's take a look at the others. Assembled from cholesterol, that's a lipid-based hormone. Able to diffuse across the plasma membrane, well, that's lipids. Lipids also dock with an intracellular receptor. That's not something that secondary messengers can do. And then promoting protein synthesis, again, that's a lipid-based hormone. All right, so only 2 here for this particular one.